Good evening and welcome to the ASV's March monthly meeting. This month we have the presentation by the ASV Lunar and Planetary Section Director, Stewart Beveridge. Stewart will be joined by fellow ASV member Barry Adcock, and following the presentation we'll be joined by Perry Vlahos, who will give us a tour of the sky for the month. But first, let me introduce you to our President, Steve Paddy. Good evening, Steve.
Thank you, Mark. Again, as Mark said, thank you for all attending and welcome to our monthly meeting. Just a few announcements before we move on with our program. The first thing that I want to talk to you about is the Messier Star Party. If you didn't make it up there, you missed what I would consider the best Star Party we've had in some time. There was plenty of games for the kids, so that they were kept busy and out of mum and dad's hair most of the afternoon, which is fantastic. We had a planetarium that was set up there for everyone to enjoy, and that went well into the night, up to around about 11 o'clock. I believe they were still hosting a program. And around about 300 people turned up. So all in all, with the number of scopes we had on the field and the main large telescopes both operating, we had a ball, and it was a wonderful event.
It certainly was. I think there is an inquiry into the young boy who won his own telescope, drew himself out of the raffle. So when we get the answer to that inquiry, we'll come back to everybody.
Okay. Unfortunately, the AGM in May looks like it's going to be an online AGM. We've tried very hard. Both Mark and Stewart have looked around the areas to try to locate a hall which didn't have the stringent conditions, or we could work around those conditions. It looks like that not only most of the halls that we've looked at are limited in numbers or aren't taking bookings, and that includes the herbarium. So we won't generally get back to a face-to-face monthly meeting till probably June, which is unfortunate. Pleased to announce that there won't be any elections this year. Thank you for everyone that put in their nominations. We have 5 new people coming onto council, and that is superb. It's nice to see new faces. That's all the announcements. So what I'd like to do is introduce Stewart. Stewart is the section director of the Lunar and Planetary Section. In conjunction with Barry Adcock, they're going to present to us a view of what they actually get up to in their section director's role, and hopefully you can enjoy the show and join the section at your leisure. So Stewart, over to you.
Thank you very much, Steve.
The floor is yours, Stewart.
Okay, so my name is Stewart Beveridge, and I'm the Section Director of the Lunar and Planetary Section. What I'd like to present tonight is the ASV Lunar and Planetary Section meetings, what the meetings look like, and what is covered. So the Lunar and Planetary meetings are divided into various parts. Firstly, ASV members send in their lunar and planetary images each month so we can compare them and talk about the conditions in which they were obtained. We also encourage our photographers to submit their images to various worldwide websites. Then, after that, we go through the planets for the month and what to expect in the upcoming weeks and months. Then Peter Thomas, who quite often joins, does a bit of a presentation on minor planets, which is very interesting, and I've learned a lot about minor planets. And one of those things is that you may have all heard that there was a second moon for a while in orbit between the Earth and the Moon, but it's now gone. Apparently, this phenomena happens quite often where meteors come through the system, get captured for a while, and go up until several months in orbit between the Earth and the Moon until the trajectory changes, and then they go back out into space again. So Peter Thomas keeps track of all these and does a great presentation. And then finally, we talk about the latest activity from various space missions, if they are related to planets or the moon. So at my last meeting, I utilised Chris Rudges Jr.'s presentation on space missions and the current missions going on at Mars. So, moving forward, here's some examples of ASV images. So up in the top right and the top left and the bottom right, we have member Cliff Ashcraft, who actually lives in New Jersey. And he's very active in sending through images from his observatory. The top left, of course, being Uranus, and the bottom being Mars. Then moving up to the top to the right, we've got an image of Jupiter there by Vince Losciovo, and then an image from Mark Justice showing what Mars looked like on the 19th of October compared to the 26th of November. And you can see a drastic change in size as Mars was moving away from us as we caught up to it and then went beyond it and left it in its orbit. Down on the left is an image from Vince of the moon. I'll just continue on. Now, the image at the top left is an image in infrared using the methane band. That was done by myself showing Jupiter. You can see, I'm not sure if you can see my cursor, but you can see the great red spot there. There's another spot here which name eludes me at the moment. And this moon up here is Io, moving out of rotation with its shadow there. Barry Adcock is going to do a presentation after mine on imaging the planets in infrared and ultraviolet, so I'll leave that up to him. This is an image of the moon from myself and Jupiter at the end of the season. Down here is an image from Morris Valamberti of Jupiter, and then this quite excellent image of Saturn is from Stefan Buddha. Then further examples is from Barry Adcock showing a multispectral image on the same night of Jupiter. As I said before, Barry's going to do a bit of a talk on this, but this is showing Jupiter starting from the left at wavelength 900, then 950, then 1000, and then 889 being the methane band, and then just an RGB image of Jupiter as a comparison. And then down in the lower left and the lower right is from Mark Justice, showing an excellent image of Jupiter and Mars. And then in the middle is another image of Vince. Now, Vince hasn't been imaging for that long, but this quite excellent image of Jupiter was taken by him through an 8-inch Schmidt Cassegrain. So to be a contributor, you don't need to have a huge scope. Of course, the bigger, the better, but even through an 8-inch, you can see there's impressive detail there on that image. And someone who's just joined recently, Andrew Amiot, has also joined the Lunar and Planetary Section, and he sent me this today, which is an excellent rendition of what Mars did last year, starting from the 26th of February, and shows it gaining in size as we went through to the 11th of October around opposition, and then again as it started to lose size going back to the 31st of Jan 2021. So why do we image the planet? So the number one reason for me is because it's great fun. The second reason is because we send off our images to compare with other associations around the world. And then we also image the planets to track any unusual changes on the planets and the moon. So, speaking of unusual changes, back on the Wednesday the 10th, an interesting object formed on Jupiter, and a number of us imaged it. And you can actually see here that in visual light, there's a bit of a smudge there. Hopefully you can see my cursor, and it corresponds to quite an obvious smudge there in infrared in the methane band. So but the night before, when Mark discovered it was there, he actually imaged it in methane between the time of 12:36 right through to 14:58. So he was imaging for quite a while, showing the rotation of this unusual feature that's just that turned up on Jupiter. So then he sent in his images to the BAA, the British Astronomical Society, and they included his image along with a number of others from around the world, showing these unusual markings, and it was very good how they all lined up. And then we see here Barry Adcock's version of his multispectral images, also showing the same object. And that's one of mine showing the object there, but it was very, very hard to see in visual light. Then again on Wednesday the 16th, the BAA contacted Barry Adcock, who's a BAA member, and reported of a new very bright spot in the Entrop zone, which must be the start of a jet stream outbreak. And then just to see what the Entrop zone is here on this diagram, it's just north of just above the North Temperate Belt, which is what NTB stands for. So the image below was where the outbreak just started, and you can see that it's quite small, and it was observed by a Japanese observer, and this was passed on to the ASV through Barry Adcock, as I said before, so that we could be on the lookout for it. Then on August the 28th, we had some nice clear skies. So myself, Morris, Barry and Vince went out to our observatories, and Morris actually rang me while I was still walking out there to say that he could spot it on the screen before even starting. And this is what that little white spot turned into. So on my image on the left matches Morris's image on the center, and then also Vince also captured that that disturbance through his 8-inch Cassegrain. And also Barry Adcock went out and also captured in multispectral images the same disturbance. So it was really good that we could image these and then send them to the BAA to add to their little library on this image. Then again on the 4th, we had clear skies in Melbourne, and I re-imaged it, and you can see that it's faint, dimmed quite a bit, or gone a bit faint compared to the few days before that. And Cliff Ashcraft, who's in the United States, they like to put Jupiter upside down, so that's why the disturbance is actually in here, but it's actually in the same place. So John Rogers from the BAA stated, "These are among the most energetic and fast-moving events that occur on Jupiter. Please observe these at all wavelengths, especially the methane band, and please monitor all longitudes ASAP, because these outbreaks often start at multiple locations simultaneously." So, what is planetary imaging? Or lucky imaging. So lucky imaging means recording video to capture hundreds or thousands of frames. Special software is then used to examine each frame and pick out the best ones that were lucky to be sharp from moments of better seeing. Using a camera with a high framing rate will allow you to capture more frames and have a better chance of getting more frames with good seeing. And that's the name of the game. After software examines the best frames, it stacks them together to improve the signal to noise ratio so they can be sharpened by sophisticated sharpening algorithms such as wavelets in Registacks. Registacks is a very popular program and has been around for some time. Most of the world's best planetary photographers are using AutoStackit, which is a program used to do the stacking. It not only stacks but aligns them and the planetary images, and Registacks then to sharpen them. But you don't have to use Registacks. There are a number of other options available. So, Lucky Imaging, here's a bit of a preview of what Mars looks like. And you can see that it's jumping around all over the place. And I would call that fairly good, reasonable to good seeing. So if you tried to take an image of that in the traditional way by taking, say, a half a second image, what you're going to end up with is not very much, because it's jumping around so much that it's just going to look very, very plain. Down the bottom left is what the image looks like after stacking is completed. And then, voila, like magic, using Registacks or another program like it, with wavelets, we use wavelet sharpening to bring out the features, which are quite dramatic here. Now, planetary imaging before Lucky Imaging was just what I said before, trying to pick the best night seeing possible and taking as shorter exposure as possible. And this is an example of an image taken in 1994 after comet Shoemaker-Levy impacted Jupiter. And this was considered to be a fairly good image in its time. But these days, I would probably think twice about presenting that, because it looks very, very fuzzy and awful. But back in 1994, that was actually a very, very good image. So frame stacking has certainly brought planetary imaging a long way, especially for the amateur. Then in 2001, looking at my favourite daily website called NASA's Astronomy Picture of the Day, an article caught my eye and described how amateurs were modifying webcams to create the best lunar and planetary images yet created. So compared to the 1990s, these images were impressive. And the webcam of choice was a CCD webcam, being a Philips 2cam. So back in the 1990s, as film was still readily available, 35mm film were purchased in plastic canisters, and these canisters just happened to have a slight taper on them and would fit beautifully into a telescope focuser set up for 1 1/4 inch eyepieces. So what people did was they took these Philips 2cams, they disconnected the lens off them, and Errol dotted on one of the film canisters and basically created a camera for their telescope, and this was the result, which I thought at the time was absolutely amazing. So what's the best telescope for planetary imaging? Starting with the Newtonian, the Newtonian is very convenient in that it has typically around a 25% central obstruction and is quite good for planetary imaging. The SCT in the middle, a Schmidt-Cassegrain, has a central obstruction around 30% and also works very well. And the refractor on the right, very good but limited in aperture due to cost. So seeing, the bottom line for high resolution planetary photography is the quality of the seeing. Seeing describes how much the image of a celestial object is affected by turbulence in the Earth's atmosphere. With good seeing, the image is steady, revealing more detail. If you don't have good seeing, it doesn't really matter if you have a terrific quality aperture telescope and perfect photographic technique. With bad seeing, you're just going to get bad images. So if I just play this, this is of a double star. I'm not sure which one it is. Whoop, I'll just go back. And you can see here that this double star looks absolutely shocking because of the condition of the seeing. Collimation. Most scopes these days are of decent optical quality, but reflectors and Schmidt-Cassegrains must be collimated correctly to perform at their best. Collimation is incredibly important and frequently neglected, especially by Schmidt-Cassegrain users. For the absolute best results, you should collimate on a star near your target every time you shoot. And I use a technique known as the bar-load laser alignment technique, but there are various other techniques out there. But I too make sure that I check my collimation before I use my telescope for every single session. Acclimation. Acclimation means letting your telescope cool down to get as close as possible to the ambient air temperature. The difference between the temperature of your mirror to ambient air is delta T. Now, delta T, if you keep your telescope inside and it's winter and you keep it inside and your house is heated, you can take your telescope outside, put it down and start observing, but the value of delta T can be as much as 20 degrees. And I can guarantee that you will not get very good images doing it that way. So if the optics of your scope are not at the air's temperature, the temperature difference will cause local seeing effects in the tube, optics boundary layer, and cause blurriness that affects the resolution of detail you can resolve on a planet. An out-of-focus video of Mars shows what the image looks like when the mirror has not properly acclimated, combined with poor seeing. So you can see here that this out-of-focus image of Mars has all sorts of ripples and awful looking stuff moving around inside the tube. So that combined with the atmospheric seeing will not give you a very good result. The donut hole is from the shadow of the secondary mirror. Heat plumes at the top are caused by the mirror not being thermally stabilized. Rapid movement from the upper left to lower right and flickering changes in brightness are caused by an upper level jet stream. And slow ripples across the image are caused by disturbances to the surface boundary layer. Focus. Spend the time to achieve good focus. Focus on a nearby star or Jupiter's moons instead of trying to focus on a low contrast planetary detail. Use an electric focuser if possible so you can closely watch the image sharpness on your computer screen. And I actually check image sharpness and focus between every single video that I do for the night. If the temperature is changing during the night, you may need to refocus periodically. And if the seeing's poor, I'll just add, getting proper focus is nearly an impossibility. Sampling. So what does sampling mean? So I thought I would show here by using diagrams rather than trying to describe it. But the minimum criteria for sampling is the Nyquist rate. What Nyquist means is that you should have a minimum of 4 pixels across your telescope's airy disk. The airy disk is the smallest area of resolution related to the size of your telescope. Generally, 4 to 6 pixels per airy disk is best. So you can see on this diagram here that there is 4 pixels covering the airy disk. So you should be able to produce good results. But here you can see that because the focal length is too short, you are actually going to miss detail because basically your pixel size is too big for the object you're trying to view. So, but what does all this mean? Let's try and simplify it. So on nights of good seeing, the general rule is to use 5 times the pixel size. So for example, if you have a camera with 4.3 micron pixels, multiply 4.3 by 5, and you get a result of 21.5. So you would want to work your telescope at about f20. So what does f20 mean? It means if you've got an f5 Newtonian, you need a Barlow of around 4 times Barlow to make it f20. Or if you've got an f10 Schmidt-Cassegrain, you need a 2 times Barlow to get to f20. But if you have a night of superb seeing and a scope of great optics, you could push the magnification up to 7 times and work at f30. Back in the 2000s, the sampling rate used to be doubled for colour cameras due to the Bayer sensor. And the Bayer sensor means that in every a group of 4 pixels, you'd have 2 green, 1 blue and 1 red. Now the sampling is the same due to advanced algorithms used in AutoStacker, and they are known as the drizzle algorithm. So to utilize the algorithm in AutoStacker and not have to use such long focal lengths for a color camera, you simply record in RAW and let AutoStacker de-Bayer and stack at the same time. Region of interest. What the region of interest means is to record only a small fraction of the sensor so you can get a faster frame rate. So a lot of people have asked why Planetary Images don't use 4K cameras with lots of pixels. And the reason that is that the object of this game is to try and freeze the atmosphere. So once you achieve your 4 or 5 pixels per Airy disk, there is no benefit from using more pixels. So I have known people who use a region of interest or an ROI of 320 by 240 on Mars, as they have very good tracking mounts. And Mars is generally quite small and typically between 10 to 25 arc seconds, but very bright. So this results in being able to run speeds approaching 500 frames per second, because you can use a very short exposure, sometimes down to one millisecond exposure. And because there's no real reason to record the space around the planet, that's why we use ROI. But sometimes we also want to increase the ROI and sacrifice FPS if, for example, we might want to record Jupiter's moons. So what do high-speed cameras look like these days? High-speed video cameras are basically still modified webcams, but you don't have to modify them anymore with Araldite. They are no longer CCD, as these days the CMOS has been developed further and further and become superior. And there's quite a few brands on the markets. And you still have the choice of one-shot color or monochrome using R, G, and B filters, red, green, and blue. You also have the option of recording in infrared or ultraviolet with various filters of each available, which Barry will talk about very shortly. If you're using an OFC camera like the ASI 224, then you'll also need an IR block filter, because this particular camera and another one that's just come out, the 462, are very, very sensitive in the IR band. So in summary, planetary imaging is actually the cheapest form of astrophotography. It can be done using the drift method without any drive at all, so long as your telescope mount is smooth. Equatorial platforms can be used instead of expensive German equatorial mounts, and also computerized altitude azimuth mounts can be used. It uses video with typical exposure settings of around 5 milliseconds. That would be for Jupiter, not for some of the fainter planets. It can be done using color cameras or mono, using red, green, and blue filters. And then on top of all this, you have to make sure that you keep your video time down due to the rotation of each planet, because Jupiter and Saturn rotate in around 10 hours, but Mars rotates slightly slower than the Earth, so you can run your video on Mars longer. But if you run your videos on Jupiter and Saturn for too long, you can create feature smudging. So just before I hand across to Barry, I'd just like to advertise that the next Lunar and Planetary meeting is on March the 19th. And because we don't have many images at the moment, because we're still waiting for the planets to return in 2021, which will probably be April or May before we get some images through. We have a guest speaker, Jim Pollock, who's the section director of the Great Melbourne Telescope Project on lunar geology. So please log into the ASV website to find the Zoom link and join us in that meeting. Thank you very much.
Thank you, Stuart. We actually have a question which I think will actually relate to what Barry's going to talk about. And the question is, what are the benefits of the different filters applied? So I think that relates to what Barry does with his filters and the imaging he does. So
I think so, yeah.
I think we can let Barry answer that one. So Barry, I'll pop your stream up and you're ready to go. The floor is yours.
Okay, can everyone hear me?
Yes, we can hear you, yes.
Yeah. Well, good evening, everyone. And Stewart mentioned the reasons why we image the solar system. It's what we like to do. But there are other reasons we do it for science. And one of the past presidents of the ASV, Bruce Poppleton, who sadly passed away quite some time ago, said that the role of the amateur astronomer is to look for the unexpected. And around the world, we have hundreds and hundreds of telescopes looking at the planets, and it's beyond the scope of all professional astronomers to keep up with that sort of thing. So amateur astronomers play a very, very important part in the solar system research. We'll start off by looking at the electromagnetic spectrum, and what I've put there is nothing. There's this little white box at the bottom. Can I get rid of that, Mark?
I don't think you can, no.
Well, I press hide and it's gone. So anyway,
there you go.
What I've started there with is a grey box, and I'm going to label it in wavelengths of light. Unlike most professional astronomers, I use SI units, so the wavelengths are written in nanometers. And to look at parts of that spectrum, we need a filter. And the simplest filter is the most common filter is the human eye. And if we place that on the spectrum, that's what we see. Now, everyone's eyes are different, so that's really just an average of what most people can see. It's considered that most people can see very, very faintly down to 400 nanometers and up to 700 nanometers. And those outside areas are defined as the ultraviolet region and the infrared region. The eye peaks at about 550 nanometers in the yellow-green part of the spectrum. And as I said, most people's eyes, well, everyone's eyes are different. And it's quite common, particularly with men, to have red colour blindness. So this red end of the spectrum is really just a sample. Now, if we turn to the modern cameras that Mark was talking about, we get a much broader and much higher region of interest of being able to detect radiation in the electromagnetic spectrum, and that's a typical. I drew that by hand, but if we move on a little bit, that's a picture of the tail end of my telescope and the camera connected to it. It's a 246 millimeter refractor, and the camera has a response to red, green, and blue light in that manner. And the camera itself, Mark mentioned the 224 and the 462 camera, both made by the ZWI company. The 462 camera is defined there as 2.1 megapixels, 2.9 micrometers square, etc., etc. And that shows the characteristics of that camera. Just moving on from that, we can purchase various filters with different characteristics, and what I've drawn there is, or what I've displayed is a set of edge filters, and what these they're all infrared filters. What this is saying is that if we pick out this one called X-Night 780, from about 750 nanometers and longer, it transmits the radiation, and 750 nanometers and shorter, it blocks it. So it really is an infrared filter. It's called different manufacturers have different names for these things, but we could call it a long wave path filter, or the cutoff frequency is considered to be around about that center as I've drawn it there. The other high wave path filter I've drawn there would be an ultraviolet filter, in that it's attenuating the light source from about 410 and longer, and it's transmitting radiation down to 280 nanometers, which is deep into the infrared, deep into the ultraviolet, I'm sorry. The other sort of filter, and the filters that I use, are called bandpass filters. And really, the human eye is a very broad bandpass filter from 400 to 700 nanometers. And I've drawn a typical bandpass filter there, centered. The center frequency there is around about 910, 905 nanometers, and its width is the full width half maximum, and in this case it's 40 nanometers. And I have purchased a set of these bandpass filters from 600 up to 1000 nanometers. And the next graph shows typically what they look like. There's the visible part of the spectrum. To the left is the ultraviolet part, to the right is infrared, and the filters that I have, that's a schematic diagram of what they transmit down into the infrared part of the spectrum. And as I indicated before, that's the true shape if you measured it with a spectrometer. Well, if we take pictures of the planets, for example, Jupiter, at various bandpass filter positions, we get a set of images which on the surface look very much the same, but they're not. And there's very subtle differences. And one of the major differences you can see here, that it's 600 nanometers, which is really quite visible to the human eye. It's almost in the orange part of the spectrum. It's vastly different to what you see at 1000 nanometers. Vastly different. The interest is emphasized if we have what we call a methane filter. Now, methane bandpass filter, first of all, that shows the typical IR blocking filter characteristics that most people have. If they use a camera, they use an IR blocking filter, and that's the characteristic there. It transmits between about 300 and 700 nanometers. A variation of that is called the L filter, which actually filters out UV light and infrared light as well. But the methane filter is a sharp bandpass filter centered on wavelength of 889 nanometers, and it's at that wavelength that the methane molecules actually absorb energy. And if we take a picture of Jupiter at 889 nanometers, everywhere there is methane will appear very dark. And that's exactly what happens. The 900 nanometer bandpass filter that I have is drawn there in red, and I also have a methane filter as well. That's a picture taken with I think that's taken with the Hubble Space Telescope using a methane filter of the planet Jupiter. We haven't been able to achieve that sort of resolution yet, but we'll have a look at what we can do. Stewart showed a few of these images before, but that's a picture of Jupiter taken at a bandpass filter of 800 nanometers, 900, 1,000, 1,000, sorry, 950, 1,000, and then the last one, top left, is the methane filter. And you can see that Jupiter takes on quite a dark presentation, and all that darkness is where there's a high concentration of methane. You can see that associated with the Great Red Spot, there is very little methane, as there is over the poles of Jupiter. The South Pole is at the bottom, North Pole at the top, and they're quite bright. And of course, none of these features show up in, well, for example, 800 nanometers or in the visual range of wavelengths. On the 4th of September 2020, the spot, the outburst of, which was thought to be an ammonia crystal outburst storm on Jupiter, occurred. Stewart mentioned that earlier. That's it there, and one can see it at the various wavelengths. That's visual light, of course. There's 600, 700, and 800 nanometers, followed by 900, 950, 1,000, and then the methane range, and then another red, green, and blue picture. And again, the difference between these is quite obvious when you look at them. Going the other way into the ultraviolet region, there are also outstanding differences. See, at long wavelengths, Great Red Spot is quite light. At the shorter wavelengths of blue and into the ultraviolet region, the Great Red Spot is particularly dark. I should mention at this stage that taking a picture, this is taken at a wavelength of 365 nanometers, well into what I call the ultraviolet region. It's of always rather dubious quality because it requires over a second exposure. There's not very much ultraviolet radiation reflected from Jupiter, so it needs an exposure in excess of 1 second, and that gives the atmosphere ample opportunity to destroy it. In addition to that, if we're limited to perhaps 2 minutes of photography, we can't take many images to stack in 2 minutes if the exposure is over 1 second of each image. So the ultraviolet image is not a very good quality, but we're working on it. 28th of September shows some interesting things. Again, there's a red, green, and blue image followed by 600, 700, and 800 nanometers. You can just see satellite IO at that point there, and you can see markings on it. It's 600 nanometers by itself. It's very difficult to see, and so it is through the region. Up in the north temperate zone, you can see this outburst again. Now, if we go on to the longer wavelengths again, what we start to see is the satellite. And it's very, very bright on the showing up on the methane image, which indicates there's no methane on the surface or in the atmosphere of Io. It's visible at 900 nanometers. It's gone again at 950, and then it appears again at 1,000 nanometers. And that may be telling us about the particle size of the soil on the surface of Io, that it scatters light around about that wavelength or absorbs it, and that's why the satellite is very, very poorly shown at that wavelength. So there's plenty of data to come out of these images. Planet Saturn is similar. If we again go through the exercise of looking at all these things, right up at 1,000 nanometers, it shows that, again, that's absorbing methane. So there's plenty of methane in the atmosphere of Saturn, but and that's why it appears dark. And so I'm just pondering over why I put that image around the wrong way. That's upside down compared to the others, but anyway, I'll fix that sometime. I've never noticed it before. Again, looking at Saturn at 800 nanometers, 900, 950, 1000, and the methane band shows very, very distinct changes. And again, as I said, that image of the body of Saturn is very dark because there is lots of methane in the atmosphere. Well, how do we detect the difference? It's all very well to look at these things and say, oh yeah, there's a slight difference here and there, but there are ways of actually emphasizing the difference. And in the time available, I've only got time to talk about one of those representations. That, again, if we look at the spectrum of the radiation and the filters which I have at my disposal, if we take images of Saturn at red, green, and blue wavelengths like that, we can put them together to form a color image, as shown there. And by the very nature of the color, it shows differences between red, green, and blue images. Now, what I've done is I've taken the red, green, and blue, and I've moved them all along. And this is what I call, in my own words, an infrared color image. That's my own personal description of it. But if I create a color picture using red, green, and blue up in the infrared region, that's a 600 nanometers, 700 nanometers, and 800 nanometers. Putting them together produces a color picture, and that, like the visible color, those colors show differences between the three images that I've shown along the top there. You can see the great red spot is orange and red around the top, and then there's some blue parts and so on. So that color image drastically shows the difference between the different wavelengths. Now, I said there on the previous slide that there was a second method that involves doing some binary arithmetic, and it's possible to actually subtract one image from another to show the difference. But I didn't intend to go through that tonight, but it takes quite some time to explain it all. So I think I've programmed it all to finish at that point.
So I don't think we've got any questions just yet. I think we've bamboozled everybody. That was very detailed, Barry. Now I understand how you go about taking your images, which is always interested me to sort of know what you do and how you do it.
Yeah, it's not meant to be a secret. It's fairly straightforward.
Oh, it's very interesting, that's for sure. So we haven't got any questions, so we might bring everybody back in. Ooh, there we go.
Yeah.
And I'll add.
Yeah, I'd like to thank Stewart and Barry for spending time putting that presentation together. We were to have a joint presentation with the meteor comment section, but unfortunately Con has work commitments tonight and couldn't make it online. So we hope to bring you his presentation sometime in the future. So I think now we can move on to Sky for the Month.
Good evening, Perry. Oh, you've got to unmute yourself, Perry. Hello? You've got to unmute yourself, Perry.
I'm unmuted, Mark.
There you go.
Good evening, everybody. Thanks for joining us tonight. I will go to my screen. I hope everybody can see that.
Yeah, it's very clear.
Okay. Now I'll just get rid of some of this. All right. Let's go to sunset this evening. And let's go to the western sky. And there's not a lot happening besides the sun. So let's advance the time a little bit, and the constellations and individual stars become more visible. Unlike the situation some months ago, where we had a number of planets in the western sky straight after sunset, currently there are almost none, except for over here in the northwest sky, and that is Mars. We had a look at it with naked eye during Sky for the Night at the Messier Star Party, which was mentioned earlier. And as Stewart and I think also Barry mentioned, it's not particularly bright at the moment because we are moving past it on an inside lane, which is our orbit, and it's falling behind because it's traveling a little bit more slowly. So for the next 18 months or thereabouts, don't expect it to be as bright as what it was during late winter and spring last year. So it doesn't make a great telescopic target either, because it's just growing smaller and smaller all the time. And as Stewart mentioned, perhaps the most important element in being able to see the planets in great detail is the atmospheric seeing. So I'll reiterate what Stewart said. The atmosphere needs to be steady to give you a good view of the planets as you get into higher magnification. The smaller the planet is, the more magnification you would have to use to get a good size out of it. And consequently, the more you also magnify the currents in an unsteady atmosphere. So by all means, have a look at Mars with naked eye and then with binoculars and a telescope, but it's only going to look a bit like that. It's not going to look as good as what it was some time ago, which is a bit like that. Or if you're using Hubble Junior, perhaps like that. So let's move on from the planets, and I'll show you which ones are worth looking at the end of this Sky for the Month presentation. Let's have a quick look around. There's the Pleiades, well worth a look naked eye or with binoculars, and even a small telescope gives you a great view of the Seven Sisters, the Pleiades. Here is probably your last opportunity to see this magnificent first magnitude northern hemisphere star, Capella, in the constellation Auriga, which is these stars here, because it will not be around for much longer. It will move under the horizon over the next few weeks, and there'll be no sight of it again until late spring this year. But above it and a little bit to the right and left, we have some visually imposing constellations. Here's the V shape of Taurus with Aldebaran there, a nice first magnitude star. A bit higher up, we have Betelgeuse. Here is Bellatrix, the belt stars, Alnitak, Alnilam, and Mintaka. Right there. The Orion Nebula here in this part of the handle. Some people say it's the end of the handle of the saucepan, but really Safe is the end of the handle. So the Orion Nebula is at the start of the handle from the pot. So this is the area you need to look at, not over here. Rigel, the blue supergiant, a little bit further over. And one of the things that we did at the Messier Star Party was trace out the river Eridanus. And it starts here with this star called Cursor right there. And it moves through these stars up to there and back down, and then does this loop, the Eridanus loop, and moves through these stars and here to Acamar, as distinct from Achenar, originally from Mediterranean and Egyptian latitudes. They couldn't see the end of the river, which is down here at Achenar. This used to be the end of the river for them. But Acamar is a star well worth having a closer look at with a telescope. It's actually one of the gems of the southern sky because it's a beautiful double star. We zoom in and there we go, splitting it into two. So Acamar, the other name of it is Theta Eridanus, is well worth having a look at. Whilst we're about it, we'll go to some other double stars that I've not pointed out in the past, which I will tonight. One of them is here with the twins, Gemini, Castor and Pollux. They're the heads of the two twins. The bodies go that way, the feet are here. There's the other twin. And Castor is, in fact, a lovely double star. Spectroscopically, we've actually been able to see that it's in fact 6 stars. But for us, with our regular backyard telescopes, we should only be able to see 2, but they are very, very close together. So you may have to wait, as we've already spoken about, nights of steady seeing for the planets and also for the best conditions to split close double stars. So the seeing is also important for double stars. Going up a little bit higher, again, the belt stars of Orion. If we sort of go to the right of them, we go past Gamma Monocerotis, and it's a hard C, by the way, not a soft C. It's not Monocerotis, it's Monocerotis. And this star, Beta Monocerotis, is a magnificent triple star. So if you've not seen a triple star before, let's have a go at splitting this guy. There's 2. Now the one that's slightly higher will split into 2 again. So have a go at beta monocarotis as well. It will be a bit challenging because these stars that I'm showing you tonight, so far at least, are pretty close to each other and could be a bit of a task for you to be able to split them. There are a few tricks that you can use in order to be able to do it, and there are many publications on double stars and websites on the web that give you quite a deal of information as to how to best go about it. But now let's head to the southern sky. And here we go. The emu is beginning to rise now, and there's the head and the beak of the emu. The neck moves through the dark lanes in the Milky Way down towards the horizon, and a little bit later in the evening, the rest of the body, again made up of no stars, but rather the dark dust lanes in the Milky Way. We'll have a closer look at that in a little while, but here is the pointers pointing to the top star of the cross, which is lying on its side there, the Southern Cross. Alpha Crucis, A Crux, is a close double star, which will be a little challenging. There is a third star involved, but it isn't actually part of the binary system, and it's further out and fainter. Also, Alpha Centauri here is quite a bit closer than what it normally is, and that may challenge small telescopes at the moment too. The Diamond Cross is found here, and above the Diamond Cross is the False Cross. Now, the 3 crosses in the southern sky are all oriented in roughly the same direction as they move around the pole. But there's the False Cross again. If you take a line from that star through this star, Delta Velorum, and extend it as far again, you come to what is called Suhail al-Muhlif, but really everybody else knows it as Rigor. Now, Rigor is probably the most easiest Wolf-Rayet star to see in the sky because it's naked eye and it's about magnitude 2 or 1.7, as it says there. And it is a fantastic double star to have a look at because there are 2 extra stars in the field not associated with the pair, but gee, they add some extra visual interest to the field. There they are. So they're the 2 extra stars that I'm talking about, and there's the binary, which is not as close together as the stars that I've already mentioned. So perhaps start with this one because it won't be quite as challenging, and you should be able to get a good view of the binaries plus those two extra stars. Now, I can remember the first time I looked at it with an 8-inch telescope, I could almost feel it was probably all in my head, as many things are, but I could almost sense that this power of this star ripping itself apart. It's a very vivid whitish colour that is well worth having a look at next time it's clear, which might be this evening. So let's zoom out of here and let's go to where the planetary interest is at the moment. And fortuitously, tomorrow morning is the best time for casual observers to look to the eastern sky and spot up, or just before we do that, I'll advance the time so that you can see the emu rising. Here we go. As it gets darker and the center of the Milky Way galaxy starts rising, and there's the body of the emu getting higher. And here we have the head stars of the Scorpion, the body with Antares there, the red supergiant, and the tail of the Scorpion winding around there. And that's up after midnight, I think. Let me check the time. Yep. Bit after midnight, Scorpius rises. We'll keep going with advancing the time, but we'll move over towards the east in a moment. And let's continue. Scorpius is up, Sagittarius is up, and we're now got Capricornus rising. And just before dawn breaks, here's the interest. A very thin crescent moon. Now, only this part of the moon is illuminated from our perspective, although at all times, if you could see it from deeper out in space, the moon is always fully illuminated, just not from our angle. So the sun is down here below the horizon and illuminating this part of the moon. But what we also have at around about 6-ish or a little bit earlier and a bit later, we've got Mercury, Jupiter, and Saturn lining up in a straight line. Let's zoom in on Mercury and have a bit of a closer look. And it should give us a slightly gibbous view of the planet at the moment. There it is. And it is highly cratered like the moon because there is very little erosion that goes on the moon and Mercury as well. A little bit higher up, as I said, is Jupiter. Let's center that and have a look at Jupiter and its moons. This is approximately the view in an 8-inch telescope. And we can go a little bit higher. The moons are Callisto down here. This would be Ganymede, Europa, and Io up here. Now I say EO because not IO, because Carl Sagan says EO. And if it's good enough for Carl, it's good enough for Perry. Damn, I'm losing it. I'm speaking of myself in the third person. Some may well say I lost it a long time ago. They could be right. But tomorrow morning, the great red spot is close to the central meridian of the planet. You can see the cloud bands there. And it'll make a wonderful sight in a small telescope. But in order to see these three planets, you don't need much, just naked eye will be sufficient. And we'll now finish off with Saturn, its rings and moons. There we go. Most people's favourite planet if we take out the Earth. So there you have it, ladies and gentlemen. If you're an early riser tomorrow, get up or set your alarm clock at 6 and get outside and have a look at this magnificent early morning view of 4 solar system objects in conjunction, very close together. Thank you for your attention.
Thank you, Perry. And I probably mentioned it before, but good old Saturn was one of the first ones I saw, and you're right, it's a beauty. Definitely my second favourite, other than Earth.
Okay, well, that concludes our presentation for tonight. Thank you, Perry, for your effort. And next month, we'll be meeting on the 14th of March, where we will look at...
April.
Oh, yes, April, 14th of April, where we'll look at public outreach in astronomy. And that's going to be presented by Mark and, I believe, Noel.
Noel, yeah. So it's more going to be about...
I just dobbed him in anyway, so he's in it now.
He knows. It'll be about our experiences with what we did last year with deep sky live stacking and streaming of deep sky, and how that links in with visually doing deep sky.
Yeah. So I hope to see you all at the Lunar and Planetary Section meeting coming up. And until then, stay safe.